Afternoon, everybody. To invite Dr. Suchetana Chatterjee, who is the Presidency University VSM meeting for a long time. After her PhD, she spent a long time in the Yale University. I think one of for the recent work has focused on the co-evolution from the context of galaxy formation in the universe. But before that, she has also worked on aspects of, say, CMB and from winds from quasars, and which have observed recently. So Suchetana, please.
Thank you very much, Vivanda. Can people hear me? Am I audible?
Yes, we can hear you. It's all right.
Okay.
You can go ahead.
Okay. So this is my great honor to be, getting the opportunity to speak at RRI in the VSM colloquium, which the students have been organizing for a long time. And I have actually attended some of their colloquium last year. So I'm really honored to be able to speak some science that I'm interested in with people who are interested about the subject. There's back-to-back exams going on, so it's really great. And thank you very much. I really thank Professor Biman Nath for such a kind introduction. And I see a lot of my students and my colleagues from other institutes attending my talk. Thank you for coming. So, sorry, I just forgot to start the video. So I'm honored to be able to present some excitement that I feel about the subject with all of you. Now, I actually prefer to sort of close the video while I'm giving the talk because somehow the slides I want to see. I hope you don't mind if I just turn off the video, and let me share my slides. Okay. So. Can you see my slides? Is it visible?
Yes, we can see.
Okay. So today, what I'm going to talk about, as Professor Nath said, is the co-evolution of supermassive black holes along with their host galaxies and dark matter. And there are mostly two aspects to this talk. So in one aspect, in the first half of the talk, what I'm going to concentrate on is the host dark matter halos of supermassive black holes. And then in the second half, we will talk about these energetic outflows that come from supermassive black holes, which have strong connection with with galaxy evolution and structure formation in the universe. And we're going to try to make a connection between the two through multi-wavelength observations and see what insights can we get from there. Now, is it not? Okay. So just this is a compulsory slide that every cosmologist or self-proclaimed cosmologists try to show. That's the cosmological model. This is the universe we live in. Now this model has some subtle issues we have heard about in the last few years that came up. And although those issues are there and yet to be settled, we have firm belief that these models sort of describes what we know about the universe today, and that's the lambda cerium cosmology. So now, in this background of lambda cerium cosmology, let us proceed and see what are the tools cosmologists or people studying galaxy evolution have to have some insights on the dynamics and evolution of the universe. Now, this is, I think, again, a sort of a compulsory slide, and the technique that I am going to use today for this talk, and which is also used in my research group, is cosmological simulations. And this is one of a very early simulation that I'm going to show you. This is a dark matter only simulation. And what we do is we have just linear perturbation theory, and then the perturbations grow through gravitational instability. And this is from Andrei Kravtsov. And what is interesting and what I want you to note in this simulation, if you haven't seen it before, is these clumpy structures in this cosmic wave, as we call the cosmic wave, the filamentary structures. And these clumpy, dense clumps that we see in this map are sort of called dark matter halos. So they are gravitationally bound objects. And I just want to point out that this simulation, this is a very old 20-year-old, maybe more, older simulation, and this is only dark matter. What I showed you is only dark matter dynamics, so we just have Newtonian gravity there. Now, as we know that the universe is not just dark matter, although that's the majority of the matter in the universe, what we really need is we need to model galaxies in cosmological simulations. Now, studying galaxies is hard, and so you have to introduce hydrodynamics into the simulation. And then I'll not go into the details of all those simulations, but we can talk about it if people are interested. So what people try to do is they have also hydrodynamics in the simulation, and they have gas particles, and then there are ways to simulate, the fluid nature of glass particles. And so those are fluid dynamics involved, although these are discrete particles or sometimes discrete grids. And then from there, what you can predict is what is the light distribution, or what is the galaxy distribution that you see in the universe. And this is again a very old plot which came after the Millennium simulation. And what you see in blue and red are essentially really observed. The blues are the real observations, and the red are the simulations, the simulated sky. That means how would galaxies look in this patch of the sky that were derived from cosmological hydrodynamic simulation. And now if you just have a glance at the map, then it seems that yes, they are kind of agreeing, which they are, except there are subtle details, and not subtle, even there are crude points that needs to be addressed. Yes, statistically, we have some good understanding, but then there are details in the astrophysics, in the gas properties that needs to be incorporated. So that itself is a very interesting and very rich problem. But then what happens is when, like 20 years back, when I was in college, of course, I did not know about these experiments. I learned them when I was in grad school, when these things became like sort of state-of-the-art discussion, is the role of supermassive black holes in the overall formation of structures in the universe, or in galaxy evolution, as Professor Nath said. So these are the correlations that were observed, the famous M sigma correlation, which showed that the black hole mass or the black hole mass of the supermass. So we know that every massive galaxy in the universe harbors supermassive black hole, and then the mass of the central supermassive black hole are somehow correlated with the velocity dispersion of stars and gas in the galaxy. Now this was puzzling because if we imagine the mass of the galaxy, then the mass of the central black hole is first quite insignificant compared to the total mass of the galaxy, number one. And number two, if we imagine the sphere of influence or the spatial scale of influence of supermassive black hole, then that's much, much smaller. That's a solar system size scale. And we are talking about gas, which are like tens or hundreds of kiloparsec away from the galaxy. So there is no reason that these gas, which are far away from this tiny, it's not tiny bit of mass, it's significant mass, but tiny compared to the mass of the galaxy. So there is no reason for the gas to sort of feel the central supermassive black hole as it has been, experiencing it, and as we see it through these correlations. So this was interesting and puzzling. at the time. But then what came up is that, okay, there must be some connection that allows the gas and the stars in the outskirts of galaxies or in the at much larger scales in the galaxy to sort of talk with the supermassive black holes, which are at the center. Sorry. So I'm very sorry about that. So then, and this is not the only observation that sort of gave us the clue. There were many others. And then,
progress.
Sorry, is there a question or something? Okay. So I'm sorry. So is it okay? Yeah. So
yeah, please go ahead.
Yeah,
go ahead.
sorry. So then these kinds of, not just this one, this is one of the famous one, and other observations actually sort of led cosmologists or people working on structure formation to think about supermassive black holes in their models. And then these paradigm that we have a dark matter halo, and then within the dark matter halo, this gas falls in the gravitational potential of the dark matter halo and forms galaxies. And then at the center of the galaxies, there are these supermassive black holes. So now this simple cartoon picture came into being, and so people started, so I showed you those cosmological simulation, and it went to the simulation community that somehow we have to know that what is the role of these supermassive black holes in the overall growth and evolution of the universe. Now, I just have a comment that if you have questions, please feel free to stop me and ask. Okay, I'm fine with that, because I think I have a lot of material. I don't know how much I can cover, but yeah, I guess we will go with the interests of the audience. Now, so in this arena, we did some work, and these are my collaborators. And then I don't know, when I think it's true for almost all faculty in the world that when they grow up, they become very proud of the work of their students. And so these are my BSc and MSc students who have been involved in the work that we did in this context, which is this is a large scale question, how are black holes connected to large scale structures? So the technique, as I said, that now in cosmological simulations, you had previously dark matter, which we saw. And then I showed you that simulation, old simulation, where you also have hydrodynamics, gas. Of course, then there is star formation that you have to include into the simulation. And then came the latest frontier in computational cosmology, is that you have to now have ways to model supermassive black hole and its overall connection with large scale structure. So this was long back. This is a simulation snapshot, and this is just a simulation box of an old simulation when I was a graduate student. This is 2008. So this is again the Millennium Group came up with a recipe. Now, I'll not talk about the recipe today, but yes, again, that's again interesting subject of computational cosmology, is how you actually model these black holes into the simulations. Because as I previously said, that we are talking about cosmological simulations, which essentially resolve scales of kiloparsec. Whereas when we are talking about black holes, we are talking about solar system scales. So there must be some technique to model supermassive black holes into your embody or in your cosmological hydrodynamic simulation. And we call them subgrid physics. So we can come to that if there are questions. Now, this is one of the older simulations. Now the field has evolved and moved forward. And so there are better techniques, better ways to in fact, much bigger box. This was a small box, 34 megaparsec box, and it involves dark matter, gas, stars. And then there is also this routine to include black holes into the simulation. Here, what I'm showing you, I don't know if how much visible this is. Here, what we see in blue is actually the wave that I showed in the previous simulation. Those are this dark matter filamentary-like structure. And then the red are the supermassive black holes all through the box. So I don't know how much that is visible through here. Here, this is a snapshot of the same box. This is at redshift 3. This is a much nicer picture. This is a projected map. Here, what you are seeing is actually the distribution of black holes. These yellow circles are actually the black holes, and the radius. Yes, please. I have been. Hello, is there a question?
No, please go ahead. I think someone was unmuted.
Okay. So here, what we are seeing in this snapshot is actually the distribution of gas, and this is actually color coded by temperature. So I don't know how much, again, that's visible, but the red ones are the hotter gas, and these yellow circles are the black holes, and the size of each circle is actually normalized by the mass of the black hole. So a bigger circle means a bigger mass black holes. So here we see the distribution of black holes with respect to dark matter. Here we see the distribution of black holes with respect to gas in the simulation volume. Now, what do we do with this? As we know that I told you that these are, so, you know, I'm not from a cosmological simulation community, but yeah, you know, if you speak to cosmological simulation people, they have, you know, a lot of understanding and confidence about, oh, you know, their codes are great and they do great stuff. But what I understand, and I think my philosophy is that no matter how beautiful your simulations are or your theoretical models are, we must have ways to sort of connect them to observations to sort of test the fidelity of our modeling. And that's kind of the step that I'm going to take in the next few slides. So now the question comes that, okay, so I have these cosmological volume simulations. I have information about dark matter. I have dark matter halos, to be more specific, because we describe that picture where we have dark matter halo, and then into the halo there is this galaxy, and then within the galaxy you have the supermassive black hole. So the formalism that we developed using the simulations actually is something that is well understood and well, you know, it's hugely popular in the galaxy evolution community. This is called the halo occupation distribution. So which means that here we will think of supermassive black holes and we will connect them with their host dark matter halos. Now, what is the crux of this formalism? So the first thing is we know that we live in a Lambda-CDM universe. We have Gaussian initial conditions. So we know the matter energy content of the universe. So essentially, we have knowledge about the homogeneous, how to model the homogeneous and isotropic universe through these. And now, the catchy thing or the loose thing is that this modeling of AGN feedback. Suppose I think about the simulation, or even when people develop semi-analytic models, it's not as well constrained or strongly understood as we understand cosmology, because this is a lot of astrophysics, a lot of nonlinear things and more complications, you know, because it involves a lot more physical processes. So in this simulation context, we have a given model of AGN feedback and evolution of supermassive black holes. I did not say what is AGN feedback. Actually, AGN feedback is essentially the outflows that sort of come out of this AGN, and that's also are modeled in the simulation. So I haven't really talked in detail about the model, but as I said, we can talk about that later. So we have these two things. Now, how do we go to observables from there? So here, the cosmology will predict what will be the dark matter halo population. That's much better understood. This is just a plot for students of how this is the mass function of halos. as a function of different redshifts. These colors are different redshifts. And then what we do is we have a probability distribution. So we know that these AGN in our simulation, or supermassive black holes in our simulation, will populate the dark matter halos. So from there, we don't look at what are the physical parameters of the model, just look at the distribution of AGN, and we can select AGN based on their luminosities. We can select AGN based on their mass. We can, like black hole mass, we can select AGN based on their Erichsen ratios. That's up to us. So let's say luminosity, because luminosity is relevant when we try to compare them with observations. So we select, so we look at the spatial distribution and the number distribution of AGN based on a certain selection in dark matter halos. So now you have the dark matter halo population. On that, you have the halo occupation distribution, which is the probability distribution. You combine this, and then what you can look at is AGN clustering. So that's essentially will tell you that dark matter, which we cannot see through light, we can understand the existence of dark matter through probes of gravity, but not through probes of electromagnetic probes. We cannot see dark matter, but we can see the spatial distribution of AGN, okay? So that we can observe. And then now, if you have an observation of AGN clustering, you can backtrack that and extract the halo occupation distribution. That is the probability distribution of how those AGN will be distributed in dark matter halos. And then you can compare with what your theoretical model predicts. So that's the work. And this is just some technical slides on how you do it, because the correlation function has two terms. The one halo term, which is black holes that are sitting in a same parent halo, and then the two halo terms, and then black holes can be, two halo term is when two black holes are sit. So one halo is, they have different halos, two halo is different halo, and then one halo is when two black holes are part of the same parent halo. So in those cases, we have to differentiate between central and satellite black holes, and then one can compute. So from this probability distribution, we can have the first moment, which is the average number of black hole per halo. We can have the second moment. In fact, we can have any number of moments. Now, if we just think of the 2-point correlation function, which is our observable, one can go to 3-point, one can go to 4-point. Those haven't been constrained observationally. Observationally, what Sloan and all these other surveys have done is they have looked at the correlation, 2-point correlation function of active galactic nuclei selected based on different properties. And so for the 2-point correlation function, we will only need the first and the second moment. And so this is the one halo term. That means when black holes are part of a single parent halo, this is the two halo term. And the other thing that we would need is the spatial distribution of black holes within a halo. So one is the number distribution. That means so central black hole, for example, either you can halo have one central black hole, or they cannot have any central black hole. For satellite black holes, of course, the numbers, we model them as something like a sub-Poisson statistics. We can just use Poisson statistics. I'm not going to get into the detail, but these shows that this dn/dm is the differential halo mass function. This is the bias of halo. This is the mat correlation function. And these are what you get from the probability distribution that we can extract from the cosmological simulations. So let's see our results. So we had a couple of papers where we tried to model the 2-point correlation function. As I said, that observationally, we have the 2-point correlation function. Observationally, we have the clustering, and we have to extract the halo occupation distribution and then compare that what we get from our cosmological simulations, the model that we predicted from our cosmological simulations of these probability distribution how does that compare with the HOD, or the probability distribution that we extract from the clustering. So here are some results. So these are two kinds of AGN that we looked at. So one was, both were at redshift 1. The first kind, this black one is actually the Sloan Digital Sky Survey quasars. So, and then these ones are X-ray selected AGN. Now the major difference between these X-ray selected AGN and the quasars was that here, these guys, the quasars, they are brighter, much brighter in optical, and they have higher bolometric luminosity. So typically, the median bolometric luminosity of the Sloan quasars was around 10 to the 46. So they are very highly accreting system, accreting almost at the Eddington limit. And then these are X-ray selected agents, so from XMM Newton, they had typical bolometric luminosities in the ballpark of 10 to the 44 arcs per second. So these were intrinsically less luminous AGN compared to this, and both were roughly at redshift 1. Of course, there were redshift distributions. Now it turns out that Sloan is a much bigger and deeper survey, so it has a lot more data. The XMM Newton 2-point correlation function that we used did not have such big samples. I'm not showing you the correlation functions, how the errors compared in both cases. But what we could derive is, we could find out the halo distribution, the host halo distribution of the X-ray AGN and the host halo distribution of the Sloan quasars. Now here what I'm showing is, in the left-hand panel, I am showing the typical, this is the median. We could get the full distribution, but here what I'm showing is the median halo mass of the X-ray AGN and the Sloan quasars. And we found that the X-ray AGN were typically sitting at higher mass halos compared to the quasars. They are almost at the similar redshift, and they are less luminous, yet they are sitting in higher mass halos. And this is actually the mean occupation function. That means mean number of AGN as a function of their host halo mass. As I said, that we found the X-ray AGN to be higher, the average number of X-ray AGNs to be higher in halo mass compared to the Sloan quasars. So what we learned from here? So what we learned is that the host halo masses of X-ray selected AGN are significantly higher than quasars at z = 1. And of course, the mean number of X-AGN per halo is higher. That can actually be connected to the duty cycle. So what it says that the duty cycle of quasars is roughly 100 times smaller than that of an X-AGN. Now, duty cycle is essentially telling us what is the lifetime or phase of that particular state we are studying. So in this case, quasars, which are very optically bright, and X-ray AGN. Now, I'll tell you that why this is interesting, and that would be the next slide. Now, it turns out that, yes, please.
I had a question in the last
Yes,
slide.
please. Yes, absolutely.
So you said that this host halo masses and this bolometric luminosity and the host halo mass relation, this left panel,
yes,
determined at redshift of 1.
Yes, roughly.
Correlation of having this redshift at some like different values like 2, 3, 4, whatever.
Yeah, so that's a very good question. Yes, please go ahead.
Yeah, what if I change the Z and what happens to the left panel? Or the
absolutely. Right? So that's essentially the next slide. Very good question. May I know your name, please? Yeah.
It's Ognivo.
Ognivo, fantastic question. So that's essentially the question that one has to answer, that, okay, we do see it redshift 1, that we see this something like a downsizing, that higher luminosity AGN, a kind of, or quasars are sitting at lower mass. What happens to other redshift? And here, so Ognivo, I don't know the answer to your question, but that is the interesting question one has to answer. Okay, so right. Here I'm showing you this is essentially this slide. So here I'm showing you a cartoon picture of what might be happening. Now, why am I showing you this is because we are used to looking at the AGN unification model. And, we have experts in the audience who actually work on AGN emission mechanism, that how are X-rays being produced in AGN, how is optical radiation produced in AGN, all this fantastic work. And we have this idea that essentially AGN are this is a unified model of AGN, that you have a same structure and it's just orientation kind of thing that determines what kind of properties are important for what kind of AGN. Now, when we connect this with this dark matter halo picture, now this is a lot of groups have been working on it. I'm preferentially showing you some of the work that we compared ours with Ryan Hickok's. This is 2009 and was sometimes at that time called the Hickok's paradigm. So what Ryan Hickok's and his group found was that they actually looked at some lower redshift AGN. So they looked at, this is redshift, typically redshift 0.5 was what Ryan looked at with, there's called AGS, AGN and Galaxy Survey, AGS. So what they found, Hickok's et al., is that the quasars in their sample were sitting at typically 10 to the 12 solar mass halos, okay? X-ray selected AGN were sitting in slightly higher mass halos, and they also had radio sample in their survey. They have radio AGN, ones which have radio jets, and they were sitting at even higher mass halos. And the proposal was that, is it likely that these AGN are the same AGN, but we are seeing them at different stages of their life cycle? That means as the halo grows, that means the host halo, as the host halo grows, is it likely that an AGN, which is sitting in a halo, is actually going from a highly accreting quasar phase? These are very low Eddington ratio systems. These are low accreting, radio AGNs are low accreting systems, whereas quasars are accreting very much at the Eddington rate. So the proposal was that, that came from that picture is that a same AGN is evolving from a quasar phase to an X-ray phase to a radio phase as its halo grows. Now, this was at redshift 0.5, as is Ognivo's question. And we could actually fill up the redshift 1. There also, what we found is that the quasars were sitting at lower mass halos than X-ray AGN. Now, of course, someone has to go to Ognivo or somebody, some of our students probably will make measurements of the, if they can make measurements of the correlation function or have ways. I know there are other ways also to find the host halos of quasars or AGN. I'll not talk about that, but I'll just mention that. But suppose we can do the same analysis, that is, we can study clustering at higher redshift of all these types of AGN, radio AGN, extra selected AGN, quasars, then we can actually test this paradigm, that is it at all the case. Now, also, we were lazy. I mean, we should have done this analysis for the radio AGN, could not find yet the right kind of sample to do this study, but that should be done to see that what is the halo mass, typical halo mass of radio loud AGN at redshift 1. Now here, if I look at increasing, this is a cartoon picture that I'm mentioning. This is no way the picture. This is a proposal and should be tested. There are many, there are many critics of this proposal who think that host halos do not have much connection with the evolution of supermassive black holes. So we can think about that later. But here in this picture, what we get, which is still an incomplete picture, is that suppose this is increasing halo mass. So as redshift progresses, that means we come from higher to lower redshift, a given halo grows. Now this low mass halo at redshift 4 might have an AGN that at redshift 4 will shine as a bright quasar. It can then, as the halo grows, shine as an X-ray AGN. It can shine as a radio AGN at a lower. So the issue is that it's likely, and what is the cause we don't know yet, but there are proposals that once the halo grows, somehow the AGN, its accretion is affected. There's less supply of cold gas in the system, and that might inhibit the accretion, and we might end up having AGN. So the halo has grown, and the AGN might just change. So it's just the same AGN that is lighting, shining as a quasar, shining as a radio AGN at different points in their life cycle, and that might have connection with the overall growth of its host dark matter halo. Ognivo, did I answer your question?
Yes, pretty much. But I had another question actually.
Yes, please.
So for let's assume one redshift. Let's assume Z almost 0.5. So I had a pretty basic question. When does an X-ray AGN turns into a radio AGN? Because as far as I know, AGN can emit in radio and X-ray simultaneously.
Absolutely right. So you're absolutely right. Yes, you're absolutely right. So when I say a radio AGN, I do not mean that it doesn't emit in X-rays. What it means is that it emits in radios. So yes, a radio AGN. And when I say just an X-ray AGN, that means they don't have any radio counterparts. So these are non-radio, this is radio. So these ones have radio jets. Does that make sense? That means what I'm saying is the turning on of radio jets, the ones that have radio jets with it, are low accreting system and likely to be sitting at high mass halos. And they have low Errington rates. So yes, they will definitely emit in X-rays too. But what makes them different from these guys is that they have additional radio emission, radio jets. Does that clarify the answer?
At some point of their evolution, the X-ray AGN actually emits in radio jets, and at that time it has also higher mass than X-ray AGN. Actually, it's 10
that's right.
Mass sun and
yes. So those are the corollary of this paradigm. That see, I'm never saying that this is the right picture. You are right. What I'm saying is that suppose it's the halo has grown in mass, then its central AGN will likely not be shining as a quasar. In its lifetime, its accretion rate will fall up, and it can shine as an X-ray bright. I'm calling it an X-ray bright AGN because, of course, we selected it through X-rays. What I really want to say here is that its luminosity is less than this guy's. It's volumetric luminosity. Now, then the volumetric luminosity might not be different, but because you have these radio jets coming, then what I'm saying is that at some point of time, these guys, the same population or a fraction of the same population, as we know that the radio fraction is low in the overall AGN picture, sort of emit in radios. When the halo grows, when there is not enough supply of coal gas and the accretion shuts down, somehow they are producing radio jets. This is the paradigm, the picture, where you are connecting the accretion of the central supermassive black hole with the overall growth of the halo. Because this is being seen. Is this correct? To say that it is correct or wrong, we need to fill up all these boxes. All of these, if you fill up and kind of get the consistent picture, then only can we say that what we are predicting is sort of close to reality. But this is a paradigm. This is a proposal. Is that fine, Ognivo? Can we proceed to the next slide? Okay. Thank you.
Hi, ma'am.
Yes,
this is Tathagato.
Yes.
So I have a question on, in these AGNs that you have selected, are there any inputs on what fraction of these are type 2s or type 1s? And if they vary with the redshift, something like that?
Okay, good question. That's actually, no, not here, but I'm going to talk about obscured and unobscured quasars in the next slide. So maybe then we can get back to your question. Okay, great. So now, as Tathagata pointed out, some interesting thing, this is the work that was led by Kostab, who did it. Most of it, he did it as his undergraduate thesis and then continued through his master's years. So what we tried to test is this orientation paradigm, this AGN unification paradigm. So we looked at obscured and unobscured quasars. Okay, and what we are trying to see is we have to study the dark matter halo masses, because in this paradigm we are always thinking that AGN is sitting in a galaxy and the galaxy is in a dark matter halo. So essentially we are looking at the dark matter halos or the large scale environments of obscured and unobscured quasars. Now the prediction is that if AGN are really described by this orientation-based unification picture, then there is no reason for any differences in the dark matter halos of obscured and unobscured quasars. And there shouldn't be any difference also if there are quasars or extra selected or radio AGN. There should not be any difference. Radio is still a little bit doubtable, but definitely selection should not have any effect on the host dark matter halos if they are from the same population. Now here we are trying to say that this is the same redshift, okay? And this is Y is selected. So you have both obscured and unobscured. And then what is shown in this plot? So there are three types of AGN here. One is, one sample is Y is selected, okay? And then they are classified into obscured and unobscured, depending on if they have optical counterparts or not. And then there is another sample, which is Sloan selected, okay? So here you see D16 obscured, D16 unobscured, R12 unobscured. And this R12 unobscured is a work done by Jonathan Richardson, who was at that time a student at Yale, and when I was a postdoc. So what Jonathan did is he looked at the Sloan quasars clustering 2-point correlation function and extracted the halo occupation distribution. So what I'm showing in this figure is actually, again, the distribution of host masses, host halo masses of this black dashed line is what Jonathan found in his modeling. This is the Sloan quasar. This is the host halo mass distribution of Sloan quasars. And then this blue and red are the host dark matter halo mass distribution of Y selected obscured and unobscured quasars. So this is for central AGN, and this is for satellite. Now the satellite was kind of unconstrained. Even for the central, what we could say is that there is some difference, as you can see that the peaks move, right? Black, blue, and red. Red has the highest peak, blue is less than that, and black is even less than that. So somehow there is difference, we found difference, yet what we can say is that the difference was modest. So what we can say is that for the central AGN, when we look at the host dark matter halos, that means these are, central means these are coming from the one halo term, sorry, so the two halo terms, so they're separate halos because every halo can have one central black hole. But the satellite occupation, although this is unconstrained, the errors were very large because of the Sloan, the wise ones, they did not have small scale clustering data that good. So we could not constrain, because to constrain the satellite fraction or the satellite host mass halos, you need a very good measurement of the 2-point correlation function to a very small scales, okay? Because you have to really get into the one halo term to measure the clustering properties. So wise measurements were not that good. But yet still, what we found is interesting, that suppose we had better measurements. This is what Kostov projected. Suppose there were better measurements of the small scale clustering of the obscured and unobscured AGN, then it showed that from the large scale clustering, what we found is that they are kind of similar. That means the orientation model, which says that obscured and unobscured can be coming from the same population, sort of is kind of respected, and it still is there. But if we look at the small scale clustering, whatever difference we got from the real data, Then Kostov made projections that suppose we can decrease our error bars much more, then we could find a very significant statistical difference between the small scale clustering of obscured and unobscured quasars, which says that you cannot just describe quasar unification or obscured and unobscured quasars only by orientation effect, because if you just have orientation, then we should not expect any differences in the host dark matter halos. So we just sort of propose some merger-based model, which I'm not discussing here. But if we can make these observations, we can predict what could be the host dark matter halos. Now, Tathagato, can you come to your question now?
My question was, are there any significant differences in the fraction of AGN that is type 2, and how does this vary with redshift? So
okay, so we haven't looked at the variation of this type 2 fraction with redshift, but this is just a single redshift. Again, this is redshift 1 observations. So now here, what we have here, there the number of obscured and unobscured, they were sort of not very different. So the number, because this is infrared selected, so they were not very different in number. Here, it's the samples were quite comparable to each other. But again, as I said, that this is just one redshift. So one can do this analysis to higher redshifts if you can have similar kind of samples at higher redshifts, which probably you might. We have to look into it, and then you can do this analysis and try to see that what the clustering measurements are predicting and what kind of host masses we are getting. So what we found is that the obscured and unobscured are kind of sitting in similar mass halos, except their satellite properties, that means their clustering properties and spatial distribution within a halo, when there are multiple obscured or multiple unobscured quasars in a halo, that is not same, and that has to have some connection with other evolutionary model, which is little bit which is not really. So I think the takeaway message which I'm putting here is that the HOD of course provides a powerful tool to sort of infer the host dark matter properties. In fact, in this case, I just spoke about mass. There are other properties that you can look at. So host dark matter mass of active galactic nuclei. And there are hints that AGN properties actually evolve with their host dark matter, or at least we can say that we do find that based on the selection of AGN, we are getting different host masses. So what could be a possible reason for that? And we painted a picture of AGN going from a bright active quasar phase to a low accretion radio AGN phase. And then with Kostov's work, we just found there were other studies which actually showed more tension with the orientation model. Our HOD approach said that yes, there is tension. It's not terrible tension because orientation is still fine, except that it cannot explain the small scale clustering, and that needs to be answered. Now, there are a lot of caveats in this work. The first is when we try to extract the halo occupation distribution or the probability distribution from the observations, there is an inherent bias in that method. And that bias is that we actually, this is model dependent. What I mean to say is that suppose I have a measurement of a 2-point correlation function. When we try to extract that, we actually have some model for this probability distribution function, which we put, and then we get the parameters of that model. So there is an intrinsic bias that we are a priori giving preference to a particular kind of distribution. So that particular kind of distribution actually came from our simulation or modeling, but there is this theoretical bias. So it's not model dependent. Nobody knows that if we used a different kind of probability distribution, will that be equally good in fitting the 2-point correlation function? So there, when those kinds of tensions were appearing, so this I do not have the time to discuss today, but we came up with something called the direct measurement of the halo occupation distribution, where you do not have any assumption of the theoretical model of the probability distribution. You just go use your crude process to match dark matter halos with AGN one by one, hand by hand, and then just measure the AGN fraction in dark matter halos as a function of halo mass. So that is more cleaner way because it doesn't have the theoretical bias, except the problem is that it can have other kinds of constraints, like cannot go to very high redshift. You do not have large samples to do that because you have to have the effective kind of samples. So this was the work that Priyanka Chakraborty, who was an MSc student with me, she did, and then previously when we proposed the method. So that's one caveat I should mention. The other is that I showed you the simulations of Tiziana Di Matteo, which is this is like 15 years back, long back the simulation came up, and a small box simulation. So many of our studies were actually based on the models that we could develop using that small box simulation. But then in the next 10 years, computational cosmology progressed a lot. And so we have much larger volume simulations. One of them was run by a colleague who is now at IOP, Nishikant Khandai. So we are now using Nishikant Khandai simulations and some other simulations that are much bigger box, where we have more statistics to sort of see that how good are our HOD model? Does it depend on simulation parameters, etc., etc.? And we can answer some of the questions based on that. So that was the first half of my talk, which is looking at the dark matter halos, and specifically at a technique which is extracting the probability distribution of host dark matter halos of active galactic nuclei using the HOD technique. So before I go to the second half, any questions, and how much time do I have? How much time can I have?
You can go, 15 more minutes you can go. Basically, it's a 1 hour talk, so you can go 15 more minutes. That's all right.
Okay. Thank you.
Because after that, we'll have a Q&A session.
Sure. Yeah. So maybe I'll have to not speak in very detail about this work, but this is another interesting aspect that's also related. So as I said, that apart from the growth of supermassive black holes, now we found that M sigma kind of correlation. So there must be some way that the black hole is talking with the large scale gas and stars in the galaxy. And from that paradigm, something that was proposed was given the name black hole feedback, which is essentially that there is a central supermassive black hole sitting in a, this was first observed in groups and cluster systems, but then people tried to extend those things, and has been also observed in galaxy systems too. So this is basically that we have this central supermassive black hole, and it's accreting, and maybe it's shining if it's an active black hole. But then if part of that accreted energy is actually giving back in the form of radiation or outflows into the intercluster or intergalactic medium. And that, you have this famous field called jet ICM connection. So that those are specifically the radio jet and the intercluster medium. And these were first observed through X-ray and radio observations. And here, this is one of the classics, like the poster child picture, a system for black holes, and looking at AGN feedback in action. And what we see here, I don't know why my arrow is not working. So this is actually an optical image of a cluster. And then on blue, the one that is overlaid on blue is actually the X-ray image of the same cluster. And then the red is the radio image of the same cluster. And we can see these radio jets coming from the central supermassive black hole. And if you carefully look at the blue diffuse X-ray gas, what you see here is there is this underluminous X-ray region, which are termed as X-ray cavities, and that's essentially these outflows are pushing the gas and creating underdense region, which sort of minimizes or lowers the extra emission from that region. And so, there's this whole industry of both theoretical, Professor Nath is actually an expert on this, so whole industry of theoretical work and observational work, both in X-rays and radio, which tried to look at this the connection of radio jets and the gas in the intercluster medium. Now, in the cosmological context, these are very interesting and exciting astrophysical systems. Now, in the cosmological context, one just can borrow this idea that what if this black hole feedback is a very ubiquitous process, and it happens at all scales of structure formation, right from galaxies to massive clusters, then that gives us a natural connection, a natural reason for the M sigma kind of correlations to exist. That now, through this feedback, through this radiation getting back into the intercluster medium, or the outflows going into the intercluster or intergalactic medium, is a way for the black hole to speak or to talk or to interact with the surrounding gas and stars in the Galaxian cluster. So to explain the M sigma kind of correlations, people also took black hole feedback as a universal and ubiquitous phenomena, which could explain physically the M sigma kind of connections. And so again, as I said, that in these cosmological simulations, one also incorporates models of feedback. And this was related to, as Professor Nath said, was my PhD thesis work looking at this feedback energy and kind of trying to find observables, cosmological observables to see, because as I said, that everything is model dependent. We have to compare with the clustering to know about the dark matter halo black hole connection. We have to compare with other observations to kind of see that this outflow feedback connection and the connection with star formation, velocity dispersion, etc. So now I'm going to briefly go through the work that has been done in my group, and then again, proud advisor of the students, so Rudrani, Korchaudhuri, and Abhinanda, they are my PhD students, and Shomo, who is now a PhD student at IUCAA, did part of his master's thesis on this, and these are my collaborators, Nishikant Tisiara and Craig Sarrazin. And so what we did is we looked at both the Demateo, as we said, that this is sort of our prototype simulation, the small one, the very first ones that tried to incorporate AGN feedback and black hole, supermassive black holes, the cosmological evolution of supermassive black holes. And also we looked at the Khandai simulation. As you can see, that particle number is greater, box size is greater. The other advantage was that Tiziana simulations actually ran up to redshift 1. Here we could go all the way to redshift 0. So these, again, these are platforms that provide us to sort of study these connections and test with observational signatures. Now, this is a slide, this is stolen from Rudrani, not stolen, she actually gave it to me. So what Rudrani found in her simulation is that due to this AGN feedback, what she showed is that if you look at two cases. Now, an observer's life is hard because the real universe doesn't give us prototype to compare our results. I think I'm getting a lot of messages. I'll look at them later. Let me finish it. Sorry. So the real world is difficult. There we don't get prototypes. But when we are doing a simulated universe, we have the advantage to sort of look at what effect this feedback is having on the gas in the cluster and galaxies. And so we had two sets of simulations. One where there was everything starting from the same initial conditions. And then there is another set, which is everything but not the AGN feedback. So one had AGN feedback, the other did not have AGN feedback, and you can tediously, it's a tedious work, but it's doable. You can just go match halo by halo, galaxy by galaxy from this set of simulation and from the other set of simulation, and compare the properties to see that what effect has AGN feedback on the gas properties. Here we are looking at gas properties only. We also looked at halo properties. I'm just showing one, just a very small aspect of Rudrani's work, where she found that once the AGN feedback is introduced in the simulation, this has been seen with other simulations also, somehow since this outflow, so this is a particular mode of feedback is incorporated in the simulation, this is called radiative feedback. So here, a part of the accretion energy actually goes and is being fed back into the gas particles, and that increases the thermal velocity of the gas. As a result of that, the gas flows away. And so the density in the vicinity of the black hole decreases, but then the temperature, the overall temperature within the vicinity of the black hole increases. So here what Rudrani showed is actually a map. So the upper ones are with feedback and the lower ones are without feedback. And the columns are, this is low mass halo, this is a higher mass halo. This is actually in the vicinity of 10 to the 12-ish. This is a little bit higher, close to 10 to the 14 solar, a few times 10 to the 13, close to 10 to the 14 solar mass halo. And what we found, and what Rudrani and we found in this work is that no matter what the halo mass is, once there is an active, this is redshift 1 result, once we have this active accretion mode in the simulation, we do see an enhancement of temperature. And of course, we also looked at the density. We did see an decrement overall. Not, this is not like one-to-one. You have to really look at it statistically. But overall, there is enhancement of gas temperature, which is likely because we are imparting more energy. But then decrease in the density of gas in the vicinity of black holes. Now, how do you connect them observationally? So one of the classic ways is the X-ray emission, as with which the AGN feedback phenomena was discovered. So Rudrani used APEC, which is the astrophysical plasma emission code, that models that if you if you put the temperature, the density and the metallicity, and this is, I'm saying it very simply, but it's a complex calculation because you have this whole simulation box, you have the central black hole, you have the millions of gas particles, and you have to smooth them, and you use certain techniques to sort of get the X-ray emission that is coming from them. We definitely don't have time to talk about all that stuff. But as I said, the Bremsstrahlung, for example, I think many of you know, is the leading X-ray emission that we see in clusters. So here in APEC, one can model the Bremsstrahlung that one will get, the radiative recombination, 2 photon, and also there are line emission, this code. So you have to couple this plasma code with the cosmological simulations. And this is what one, just example of one system where Rudrani computed what would be the projected X-ray emission that is coming from these, from when we include AGN feedback. So you can make a map of X-ray without AGN feedback, and you can make one where there is AGN feedback. And you have to repeat it for all the system, because one system can have some features that really doesn't tell us much, but definitely you have to go system by system. You have to do it for multiple redshifts to see if there is any redshift evolution. You have to use different kinds of halos to see. So all these things have to be done. And then statistically, what one can do is you actually look at all the systems. Maybe you do a cutoff, like you can cut off based on the black hole mass, that you're going to only select halos which host black holes of mass greater than 10 to the 7 solar mass. Or you can choose that we are going to only look at black holes which have certain threshold frequencies. So you make a selection which is observationally relevant, and then you stack all of them and find the average theoretical profile, the radial profile. As we say that if I look at this map and look at the radial profile of what would be the X-ray emission between with and without feedback. And what we found is that typically, this is an example, this is a theoretical profile for this redshift 1. And what we typically find is that at smaller scales, we do see a suppression of X-ray flux. And that's mostly because of the low density, that when you heat up the gas just escapes the potential well from that area. And that sort of lowers like a cavity, as you can see. So the black hole is sitting right at the center, and you can see this cavity kind of thing. And that is being sort of ubiquitously seen in all systems around all redshifts in the simulation. Now, there are a lot of details to it. I do not have time. I have to quickly finish up. And this is actually a synthetic X-ray observation. So just not the theoretical map, but once you want to see them in a telescope, is it possible to anyway resolve these differences? And so what Rudrani did is she actually took the theoretical map and then did all these, something we called synthetic observations. So she used marks to simulate that how would this observation be seen if we had the chance to see it from a Chandra simulation. So you have to put up the observing time, you have to tune your detectors, and this is actually a photon map. This is a Chandra photon map, and that we get. And the thing is that it's tentative. If we come to low redshift systems, we still have a lot of Chandra ability to detect the difference between with and without feedback cases. For high redshift objects, there are issues with some spatial scales. So I'm not getting, as I said, that there are a lot of details into it. And then I'll just quickly end my talk. I don't have time to work on it. Is just not the X-ray. The other interesting thing that one can do is looking at the CMB distortion that this hot gas will produce. We are talking about these energetic outflows from the black holes. And these energetic outflows can interact with the cosmic microwave background, which was my PhD thesis, and we can get a signal through the inverse Compton scattering of the CMB photons through the Sunyaev-Zel'dovich effect. And this was a long back prediction from my thesis work. We predicted that there can be a microkelvin level distortion in the CMB due to Sunyaev-Zel'dovich effect from AGN feedback. Of course, it depends on the model of AGN feedback, as I have been always saying. And these are some of the predictions that we made, that we can detect this signal through direct millimeter wave observations, through statistically, by cross-correlating CMB maps with surveys of quasars, etc. And there were a lot of detections. I'm very proud to say that in 2019, there was the first detection of Sunyaev-Zel'dovich effect, direct detection of Sunyaev-Zel'dovich effect from quasar feedback using the ALMA, the Atacama Large Millimeter Array Telescope. This was led by my colleague Mark Lacy, and these are some references of detections through cross correlations that happened in the last 5-6 years. Now, what we are trying to do, and this is a work that is my another PhD student, Ovinanda Chakraborty, is leading, is we are just like we are looking at the X-ray emission in AGN, we kind of try to use the same simulations and look at the SZ emission. Now, why do we want to look at both SZ and X-ray? Because then, so this is an example of, this is a SC map, okay? This is in Jansky, and this is an X-ray map of the same feedback system, same black hole system in the simulation. This is a large map, 300 kiloparsec by 300 kiloparsec map. And then we can make projections that how will this signal look in, for example, ALMA or NGVLA, and try to see that if we can detect this signal. And of course, there is the X-ray emissions, as Athena is coming online, Chandra, of course, is there. And then once you have, the reason that we want to do a joint SZ and X-ray analysis is because, as I said, that puts more constraint on the models of feedback that we are using, and overall in what is our understanding of connecting black hole systems, their feedback mechanism, their growth with the overall structure formation in the universe. Now, this is sort of the summary of this part of the work, that we can look at SZ and X-ray signals from AGN feedback, jointly model them, and use the synthetic observations technique and try to detect them with upcoming and ongoing and upcoming X-ray and submillimeter missions. Now, thank you. So before I end the talk, I think the talk officially ends here, but I want to show you, as I was telling, that what is the state of computational cosmology today. So I want to do that, and that's why I want to show you this kind of recent, not exactly recent, but quite recent simulation, the illustrious simulation, which has this extensive way of modeling different modes of feedback and what effects. So I just want to end my talk by showing this simulation, if I'm given 1 or 2 minutes. So just one sec. Now, can you hear the sound? Because is the sound audible?
Yes, yes. Can you just go about again?
Or I have to share the sound. Just a sec. I think I have to, in the share screen, share computer sound. Okay, share. Okay, so let's start. This is the illustrious simulation, and you can go and look up it. Essentially, you can actually go to the level of, simulating like galaxies and galaxy shapes. And then, of course, all the things that we discussed in this talk in the simulation. Okay. So I think I will stop here and questions now. Thank you very much.
Thank you, Suchetana, for the very interesting talk. Lots of interesting stuff, new stuff. So are there any questions, comments?
I see a question in the chat box.
Yes, we can come to that.
But I think it's up to the organizers.
We can come to that later. That's about wormholes.
Yeah.
Let's take some more relevant questions.
Ma'am, I had one
some questions, but I'll ask later.
Yes, please. Who is this? Somebody had a question.
I had one query.
Yes, please.
Can you go back to the slide where you share, like, kind of compared the with feedback without feedback plot?
Yes, just a sec. Let me just now move from, yeah. So with and without feedback. Yes, yes, this one. You're talking about this one, right?
So we see a dip at around 1 arc second from the center,
Yeah.
then it grows
Yeah.
back, and then it goes down again. So this dip
That's
is
right.
due to that you basically said because this hot gas is hot, so that's why it gets dispersed from the center.
Yes.
So is that signature, this dip?
Are you talking about this one or?
Before the peak, there is a dip, right?
Yeah, there's a tip. So what happens? So if we see this picture, this is also only one system, but even this system will explain what you said is exactly true, that it's in this small scale. You see that there is a dip in X-ray, right? And that's essential because although the gas is hot, we do see a hot gas. That means the temperature of the gas is higher. Right. But since this gas is getting this additional kinetic energy, because that's how it's modeled when we redistribute the feedback energy, as we call, which is 5% of the radiated energy. So to redistribute it to the gas, and that's also done according to a smoothing kernel. So this gas gets additional energy, and that's why it just moves away. And that's why we do see the density decreasing. I haven't shown you the density map, but if you go and look at Rudrani's paper, she actually also has plots of the density. So the density decreases, but the temperature increases. But then the X-ray actually is dominated by the thermal Bremsstrahlung, which causes n squared t to the half. So there, the density business actually takes more effect. That since you have lower density, the X-ray goes away. That we see sort of ubiquitously in all the systems. That's not the case when we're looking at Sunyaev-Zel'dovich, because Sunyaev-Zel'dovich, if you look at the equation, it's actually n times T. So it's the pressure. So this is density times temperature, whereas Bremsstrahlung was n squared T to the half. So here, density and temperature has equal contribution. This goes down, this goes up. But then overall, we saw that the Sunyaev-Zel'dovich signal actually is going up, whereas the X-ray signal is going down. Does that answer your question? Yeah.
So can you please go back to the plot? I just add something.
Yes, sure.
Yeah. So at around 1.5 arc second, we see a peak. At 1 arc second, we see a dip. So this is due to basically this gas is hot, basically.
Yeah, this peak, I'm still doubtful about why would such a peak appear, and because if it's statistical, but you're right, the gas is being pushed at the surrounding.
Yes, this peak is due to the feedback, right?
Yes. Now the point is this scales, which is 1 arc second or 1.5 arc second, this scales is actually, it will depend on the redshift of the system. For example, typically these scales are, it's around tens of kiloparsec. Now this whole map is 50 kiloparsec. So if we have a bigger map, then it's better to see. So typically the scale is tens of kiloparsec. And this is since redshift 1 object. So when you convert into angular scale, you get a very, just 1 arc second, which is sort of at the nominal resolution of Chandra. So you really don't have much chance to detect. But then these scales will increase once we come to more nearby objects. And then you have better chance to observationally detect these differences. So the scale, 1 arc second, 1.5 arc second, is dependent on the redshift of the object. But I think better to say is that it's tens of kiloparsec is the typical, the co-moving scale. The tens of kiloparsec is the scale of influence that we are seeing. Not that all systems are tens of kiloparsec, but that's sort of the average.
Right.
Okay. Sorry, is that okay?
Yeah, it's all right. Okay, thank you.
So Suchetana, how are you depositing energy? I mean, you said there's a kinetic energy being converted to thermal, or are you doing it radiatively by Compton heating or something?
Yeah, so that's a good question. So I shouldn't, although it's called radiative feedback, it's not done that way. So it's not Compton heating. So what we are doing is we have m dot c square is the accretion energy. Now, if you multiply by eta, so let's say if we use 0.1, so this 0.1 m dot c square is kind of the bolometric luminosity of the AGN. Then 5% of that, so 5% of that bolometric energy, that is now deposited into the gas particles, which is essentially increasing the thermal energy of the gas particles itself. So, so it's the total energy. Now, how do you distribute it in the surrounding?
But what is the microphysics you have that?
I think that's the best question. So the microphysics right now is not there, because that's what is, I don't know, we don't have so much understanding, first of all, that what is this coupling that would actually do the feedback. And, you have people doing analytic modeling of what could be this microphysics. Here, you just think that by some means the gas couples and you just redistribute. Then you may ask that, how do you know how much gas to couple, how much energy to couple, etc. So the justification to that is the way you do it, like what would be the feedback fraction? How do you know that 5% of it is coupling? So the justification to that, as this is not my simulation, I mean the people who ran the simulation, is they tune these parameters to m sigma relations,
I see.
to the luminosity functions of luminosity functions of galaxies and agents. So you look at these, so it's observationally tuned parameters, not coming from microphysics.
But there could be a lot of interesting microphysics going on in the vicinity.
Yes, absolutely.
The inverse Compton cooling would zap the energy of the gas very in the vicinity.
Yeah, so the microphysics will be very interesting. Now, the cosmological simulation is not the best tool to do that, because we are only simulating scales which are kiloparsec to sub-kiloparsec. And here, when you have to do the microphysics, you have to really go to the accretion disk level scales. So then you may ask, the point that I was trying to make, that how do you even model these things? And so this is subgrid physics, that the physics is happening at a scale much below the resolution scale of the simulation, and you just have some way to extrapolate it to these large scales to match the observations.
There are some questions. There's some Shogata.
Some questions?
And Aditi.
Yeah.
Yes, please.
Okay. Can I ask one question? Hello?
I'm fine to answer all questions. It depends on Professor Nath.
Okay, ma'am. So you showed a few slides back, I think, that there is a relation between the AGN luminosity and the halo mass, right? I mean,
this one?
Yes. Yeah. So let's say, I mean, if you have a lower luminosity, you have more kind of, mass in this case. Now, let's say this AGN reaches the Eddington luminosity in some scenario. Does it somehow affect this relation to the mass? I mean, does it have some extra effect on it, or?
Okay, so what I'm showing here I'm not showing any relation between halo mass and bolometric luminosity. Now, so two things. One is, if you go into the simulation, then you can actually look at because there is a specific way. I've never told you that how the black holes are simulated in the system. So there are specific ways to put black holes in halos, and now these black holes will actually, in the simulation, they do Bondi kind of accretion. So but then in the simulation or in semi-analytic approaches, can you hear me, folks?
Yes.
I should stop sharing. Am I audible? Because yes. So one can always come up. So depending on how you model AGN in your simulations, or suppose, as Professor Nath was saying, you have analytic or semi-analytic techniques to model the physics, you can still, well, not microphysics. When we are talking about halos, it's not microphysics really, but you can have your own model on how the bolometric luminosity of AGN may vary as a function of halos. What I'm showing here is not a relation. What I'm showing here is that I just look at two sets of AGN, one which are quasars and are detected through optical surveys like Sloan. In the others are AGN that are bright in the X-rays, which are detected in XMM Newton in X-ray surveys. And you look at their large-scale clustering properties, and from there you derive their host mass halos. So that is an observationally determined only two parameters. I shouldn't say that what it shows just that for these two sets of AGN, I see that the ones having higher bolometric luminosity actually are residing in lower halo mass. Is it true for, does it give us any clue on what could be the relation of bolometric luminosity and halo mass? My answer is no. It gives us some hint that maybe it is the case that more luminous AGN are preferring to sit at higher halo mass. Theoretically, why would you expect that? There are some theories for which you can expect that. But your question is that suppose an AGN is accreting at the Eddington rate.
Yeah.
How? So, for example, my quasars, the ones that have 10 to the 46, that's the median bolometric luminosity. They were even 10 to the 47. So they were at Eddington rate or just, I mean, it's close to Eddington. So they were very near to doing Eddington accretion. And what we found, just not this study, but many studies found that quasars, preferentially, I think this is also related to Ognivo's question, partly, is that quasars in particular, which are very bright AGN and which are accreting at the Eddington rates, over redshifts preferentially sits at halos in that mass scale, in the 10 to the 12, 5 times 10 to the 12, 10 to the 4 times 10 to the 12, the mass scale that we found. It's not just redshift 1, but in all redshifts, quasars somehow prefer to sit in that halo mass. So I don't know if I answered your question because...
Yes.
Okay, thank you.
Yeah. Okay.
The question from Shaugata.
Hi, ma'am. It was a wonderful talk.
Thank you.
I was wondering that you showed the famous M sigma relation, which is the motivation to include feedback. I was wondering that the state-of-the-art simulations, how far along are they in reproducing a plot like this from simulations?
Okay, good question. So first I have to tell you that M sigma is one of the many motivations for including AGN feedback into galaxies and overall cosmological simulations. The other one, there are many others. The other that is very famous, some of you might have seen it, is when people look at the galaxy luminosity functions and they see that there is mismatch of the galaxy luminosity function with the halo mass function. So if you just make a one-to-one correspondence between mass to light, then you do see a mismatch between the mass function of halos and the luminosity function of galaxies. And then at the high mass end of the galaxy luminosity function, you actually include AGN feedback to match with the observation. So there are a couple of reasons why AGN feedback. Now your question is that how accurate are current simulations in predicting M sigma kind of correlations? So this is a very good question. But I think, for example, if I look at DiMatteo's work, which was work back 10, 12 years back, 15 years back. So they were not predicting the M sigma relation. Actually, they were, let me tell you how they did it. So I just answered Professor Nath's question that suppose I tune my feedback parameter, that how much energy am I feeding it into the intercluster or intergalactic medium. That's a free parameter in my simulation. Now, how do I fix the free parameter? Now, what DiMatteo's group did is they looked at the local M sigma relation. So they actually looked at lots and lots of isolated simulations and tried to tune their feedback parameters in such a way so that it reproduces the local M sigma relation. And then, so then that fixes the free parameters. Now, using the simulation, because that's fixed throughout the simulation, now using the simulation, you can predict that, suppose I normalize my simulation with the local M sigma relation, can I predict its redshift evolution? Or can I predict the galaxy luminosity function or the AGN luminosity function? And then if that matches with the observations, then I can say that I'm doing a decent job. Also, the opposite can be done, that you sort of fix your simulation based, because these simulations are not like, this is basic level calculation, right? It's not like you don't do the calculations from the fundamental levels. As I said, that you don't even resolve those scales. It's subgrid physics. So you have to rely on one or two observations to fix your parameters, to tune your parameters. But then the good thing is that you can always have another set of observations that you can predict. And then you fix your parameters on the M sigma relation and you predict the galaxy luminosity function. If they come out to be reasonable, then you can kind of be confident that, okay, you are doing a decent job with the simulation. So does that answer your question, Shogata?
Yes, thank you.
Mm-hmm.
There was a question from Aditi, but I don't know whether she's around still.
No, I think I think we can pass this.
It's a question from Desh. Hi, Desh.
Hi.
This is the last question. You can take that.
Okay. Yeah, thanks for the talk. Very interesting. The radial profile that you showed, I just had one comment. Given the morphology of the jet, the very last.
Yeah, I'm coming to that. Yeah, I know which one you mean. Yes, please.
Yeah. Given that the void will be created, corresponding to the jet morphology, it's always going to be, not going to have circular symmetry in the projection.
Yes.
Right. So you might actually find that if you allow for that, it's like an ellipsoidal cavity and have the normalized distances, you might find much significant contrast than you see here. And that might it's a message that might get hidden because of this, circular.
So that's a very, So that's a very good point. Now I want to mention one thing, that in the simulation, the one that both Nishikant Khandai's simulation and DiMatteo's simulation, there, this deposition of feedback energy, as we were talking, the way it is done is, it's actually done isotropically. So it's not really an isotropic jet mode that they are simulating in the simulations. This is actually isotropic, and that is related to the geometry of the cavities or the the X-ray overdensity, X-ray overflux, etc. that we are getting. But if it is anisotropic, then definitely that will have signature in the both. Of course, in the maps there will be the signature, as Desh is saying, that you have this ellipsoid kind of models, and of course that will be reflected into the surface brightness profiles, or the radial profiles. So Rudrani, in her thesis, she just had in her thesis, and now she's working on the paper. She's looking at so Ramil Dave and his group. This is a 2019 simulation that they have done, where they included many modes of feedback, not just this radiative isotropic feedback, but many modes of feedback. And Rudrani is actually trying to see that what is the effect on the X-ray surface brightness profile, let's say, or the X-ray flux images, if we switch on different modes of feedback. So that's a very good point. Yes, this is sensitive to the model that we use in the simulation. Here, in this case, it's just isotropic feedback, and that's reflected in the geometry.
Yeah, thanks.
Thank you. Yeah.
Okay,
Any other questions? Okay, so I see some questions from some of the students of Presidency. They can always ask me at other times. But yeah.
So let's thank Suchetana for the wonderful talk. Thank you, Suchetana.
Thank you so much, Professor Nath, and also thanks to everybody who has been there for such a long time and hearing the talk. So I would say that stay tuned. Today only we got so many papers from Erosita coming on the archive. So Erosita, for example, will be essential and useful to test some of our models and studies that we did. And I think it's an exciting time to study the intergalactic medium or the intercluster medium, both through X-rays and of course sub-millimeter wave, as you all know. So, because I see a lot of youngsters in the audience, so I wanted to keep that message. Thank you so much.
Right.
Yeah.
Thank you.
Okay. Okay. Thank you. So can I leave the meeting now? Yeah.
Yes, ma'am. Yeah, you can leave. I also want to ask everyone present here to just unmute their mic and clap because we have to do this online.
Oh, thank you so much. Thank you. It's very nice. I wish so online is good, but I think going there and giving the talk is much better. Yeah.
Yeah. Oh, now we have to
so hopefully we'll do that one day. Thank you so much. Yeah.
Sure.
Thank you, Bimanda, and others. Yeah. I think Jayant was here. Moshumidi was here.
Okay. Thank you, everyone.